in DC. My name is Bob Rich, and I'm the Executive Director of the Arctic Research Consortium of the United States. And welcome everyone, both face-to-face and virtually, to the DC office of ARCUS, the Arctic Research Consortium of the US. ARCUS has been working for more than 25 years to connect Arctic research across boundaries through communication, coordination, and collaboration. We're a nonprofit consortium of organizations and individuals interested in advancing inquiry, discovery, and understanding of this important region and informing sound decision-making. The seminar series has been conceived as an opportunity to provide unique access to some of the leading Arctic researchers for federal officials, members of the DC policy community, and the broader public interested in the changing Arctic. The ideas shared here represent the cutting edge of what we're exploring and learning up north, and also what it means for the U.S. and the rest of the world. I'd encourage you to take a look at the ARCUS materials you were handed if you're here face-to-face, or if you're online, to visit our website at www.arcus.org shortly after the presentation. After the presentation, I'll be happy to answer any questions and love to hear how we can help you to succeed in whatever you're doing related to the Arctic and research. We're joined here by more than 100 participants online from around the United States, as well as throughout Europe, Asia, Pacific, other places, Canada, and we're glad that you're all here with us. For those of you on the webinar, my colleagues are available online to answer any questions you have about the seminar, about ARCUS or Arctic research. Just type your questions into the question box on the right-hand side of your screen. But whether you're here or online, we invite each of you to become an ARCUS member. Currently, academic institutions, government agencies, corporations, and indigenous organizations are all eligible to become ARCUS members. Also, any individual who cares about the importance of Arctic research can become an individual ARCUS member. And you can join us on our website or talk to me afterwards, and we're happy to sign you up. So now let me introduce our speaker for today. Dr. Jennifer Francis earned a BS in meteorology from San Jose State University and a PhD in atmospheric science from the University of Washington in 1994. As a professor at Rutgers University since 1994, she taught courses in satellite remote sensing and climate change issues, and also co-founded and co-directed the Rutgers Climate and Environmental Change Initiative. Presently, she's a research professor with the Rutgers Department of Marine and Coastal Sciences, where she studies Arctic climate change and Arctic global climate linkages. Her talk today is entitled Crazy Weather and the Arctic Meltdown. Are they connected? Please join me in welcoming Jennifer Francis.
Turn my microphone on, right? Hello, everyone, here and afar. So I think it's fair to say that Mother Nature has not disappointed us this winter. We were expecting some pretty interesting weather. We knew we had this El Nino brewing out in the Pacific. We knew that sea ice was running quite low. And a lot of other things were going on in the system that were quite unusual. So I mean, think back to those of us in the Northeast. We were out picking out our Christmas trees in December in shirt sleeves, right? And right through New Year's Eve, we still kept those shirt sleeves on, right? That was a pretty unusual thing. December was a record warm year in this part of the world. And then in January, we saw some very unusual flooding in the middle of our country, Texas and the Mississippi Valley, due to very persistent rainfall in that area. And then you all here in DC were treated to Jonas, that little snowstorm here in New York, and that was very exciting. And since then, you know, we had a big blast of record-breaking cold air here, while out west they've been dealing with record-breaking heat. So as I said, Mother Nature has not disappointed us. So what we're going to talk about today is how some of this crazy weather that's been happening over the last really couple decades now going back perhaps is related to the very warm Arctic that we're experiencing. So this is going back now to last winter, looking at what Boston was like for much of January and February. There was just snowstorm after snowstorm after snowstorm. And I have a lot of friends and relatives who live up in this part of the country. And they were actually, you know, Bostonians and New Englanders are pretty tough, but they were really upset. I mean, this was, they were really tired of this snow. And the people who knew what I did for a living were actually getting quite angry and were starting to send me emails. And, you know, I was waiting for a dead goat to show up on my front lawn. And a good friend of mine took pity on me, heard what I was dealing with, and sent me this cartoon, which seemed to kind of sum things up pretty well for how people were thinking last winter. So we don't have to look back very far in time to see a very different story. So last winter was 2014-15. Here we have January through March of 2012. And all of those red states in the east there are all reporting their warmest ever winter. So just a few years ago, a very different story. We'll come back to this in the end. But we are not alone. It's not just the United States. So the UK, for the last 3 winters now, has been dealing with some very unusually stormy conditions. Some record precipitation events, which is saying a lot because their precipitation records go back 250 years. We've seen places that are used to getting a lot of snow, like this area in Japan, in this particular year of 2012, got a record amount of snow. And, you know, I'd love to see the snowplow that they have for this road. It's just really hard to imagine. There have been, as I mentioned, here in the States, we've had our flooding situations. Well, there's been a lot of flooding events all around Eurasia, North America. You can name a lot of them. And of course, we know California is dealing with probably the worst drought it's ever experienced. There were high hopes that El Nino was going to alleviate this drought. It's made a dent, but so far that promised heavy rainfall has really not occurred. And we'll come back to this in the end too. So we scientists are not alone in track of these increasing extreme weather events that we've been experiencing. The reinsurance industry is very interested in extreme events because, of course, they have to shell out a lot of money when they happen. So this is from Munich Re, a reinsurance company, so they insure other insurance companies. And what they've done is an analysis going back to 1980 and looked at the occurrence of different kinds of extreme events. So the red bars down at the very bottom there are the kinds of events that are due to things like earthquakes and tsunamis and sort of geophysical type events. The other ones, the green, the blue, and the gold, are all related to weather. So what you notice is that the geophysical events have not increased in frequency, but the others certainly have. So there are certain kinds of extreme events that I'm going to be talking about today. And what they have in common is that they're all related to weather patterns that are very persistent. Okay, so the California drought is a great example. If you don't have rain for a couple of weeks, no problem. But when it goes on for, you know, now 3-4 years, it becomes a huge problem. So these are the kinds of extreme events that we've been looking at in relation to what's been happening in the Arctic. Okay? Good to keep that in mind. So some of the good news, if you can call it that, that is related to the increase in extreme events is that the public is noticing. They're noticing that their weather is changing. And they see that it's not the same that it used to be. It's weird. And they're starting to ask, you know, what the heck is going on? The media is all over this. And in particular, they're wondering whether there might be some connection with climate change. Well, this was a sticky question up until, say, 5 years ago, because there really hadn't been that many studies that made connections between extreme weather and things that are happening in the climate system. But there have been a lot of studies just in the last, say, 5-7 years. So now that I think most scientists who are looking at this problem are very comfortable answering this question now, when before we really weren't. And now I think most of us are very happily saying, absolutely, there's a connection. So let's just step back in time a little bit here and step back and take a little bigger look at the situation and put it into context. So here's a plot that I'm sure many of you have seen some version of. We're looking back about 1,000 years and looking at how the global amount of carbon dioxide in the atmosphere, which is in blue, and the global temperature have changed over these last 1,000 years or so. And of course, what you notice is that as we go from the left part of the curve towards the right, we're going closer to the present day. Actually, the global temperatures were going down. And that is related to some changes in the orbit of the Earth. I mean, this was part of the natural climate cycle. And then as you get, of course, close to the present day, what we find is that, of course, the temperature of the Earth is rising rapidly, as is the amount of carbon dioxide in the atmosphere. We all know that this is because we're burning so many fossil fuels and putting that carbon dioxide in the atmosphere. But if we bring this to present day here, and we look at the amount of carbon dioxide and the global temperature, what we know now is that the amount of carbon dioxide that's in the atmosphere today is the highest it's been in at least 2 million years. It's really quite staggering. And we know the global temperature is starting to respond to that. But we also know that it's not responding uniformly around the Earth. Some parts are warming faster than others. So this is showing just the differences from normal in temperature. And what you see is that the yellows and reds and browns there are all showing us that the globe as a whole is warming, but the biggest warming is happening in the Arctic. We can zoom in on this in another way and look at just the winter temperatures in the Arctic. And this is now showing trends in the temperature. And again, you see that the trends are largest in the Arctic. It's warming fastest there. But also some other interesting features start to emerge when you just look at the winter. You see that it's actually cooling in Eurasia and over North America. So we'll talk about that a little more later. All right. And, you know, some people still wonder, you know, how we know for sure that humans are causing this. Well, one of the best tools that we have to answer that question are these very sophisticated global climate models. They're computer models that simulate a variety of processes that happen in the climate system. They simulate weather, they simulate ocean changes and currents and snow and sea ice and all the things that happen in the real world, or most of the things that happen in the real world. So we can use these computer models and look at how they simulate the Earth's temperature when we tell it about things that have happened in the real world. So things like volcanic eruptions, how the sun has changed over time. And when we do that, we look at this simulation by the models going back to the 1900s, which is in the blue line there. And it does a really good job compared to the observations, which are in black. So up until about the 1960s. And then we see that the real world in black and the model simulation diverge. And why is that? It's because we haven't told the computer model that greenhouse gases are increasing. And when we do that, we see that the two compare very well. The models capture very well what's happened in the real world. So we have some other ways of detecting the human imprint on the climate system as well, but this is one of the best and most reliable ones. So not only is the Earth's temperature increasing, but we're also seeing an increasing amount of water vapor in the atmosphere. This is completely expected because as you warm air, more water vapor can exist in that air. And so we're seeing about a 7% increase in the amount of water vapor in the atmosphere. And this is huge because that water vapor is a really important part of the climate system. It does a bunch of things. First of all, it provides fuel for storms. When that water vapor condenses as a part of rising motions in a storm, it releases heat, it releases energy, and that fuels storms, in particular hurricanes. It also, water vapor is a strong greenhouse gas. So as we increase carbon dioxide, we warm the planet, it adds more water vapor in the atmosphere, it increases the greenhouse effect. So this is what we call a positive feedback in the system. It adds to that trapped heat that the carbon dioxide is doing as well. And finally, that extra water vapor is available for precipitation. And so what we're seeing around, especially the United States, is an increase in the frequency of heavy precipitation events. And that's what's being shown in this graphic. So in the eastern part of the United States in particular, we're seeing a big uptick in the frequency of these very heavy precipitation events. All right, so that's all sort of global background. Let's shift into talking more about the Arctic now. There's a lot of change going on in the Arctic. One of the most concerning ones has to do with Greenland. So if we look back to 1992, which is the far left image of Greenland there, what we're looking at in orange is where the surface of Greenland melted sometime during the summer of that particular year. So 1 decade later, in 2002, we see that area of orange has dramatically increased. And then if we move over to 2005, just a couple of years later, again it has increased. And in 2012, almost the entire surface of Greenland underwent some melt that year. This is a real concern because when the ice in Greenland melts, it goes into the ocean and it contributes to sea level rise. And if we look at how the mass of all the ice in Greenland has been changing, some very recent work by Marco Tedesco, we see that there's a very steady downward trend in this estimate of the mass of ice on Greenland. So this is a big concern for sea level rise. Why? Stop! What are you doing? Oh no. I don't know what happened. This is very odd. Okay. I'll ask it to go back. One slide. Didn't seem like a lot to ask. Sorry, everybody. There we go. Yay. All right. So, the X or Y?
The Y.
The Y. This is gigatons of ice. So literally the mass of ice on Greenland.
So there's negative ice now?
Well, these are anomalies, okay? So relative to the normal, relative to average over the time period. Okay, little technical interlude there. All right, so as I was saying, we also know things are happening with the glaciers all around the world. So here's a picture of a glacier in Australia back in 1875. That very same glacier, about 125 years later, is basically gone. And if we look around the world at what's happening to glaciers all over the place, so these plots are showing how glacier mass has changed going back to 1960 or so, and it includes Europe and the Andes and the Arctic and all over the place, Patagonia. You can see that they're all basically in massive decline. One of the things that we're realizing, we think, is that the extra meltwater from both glaciers and Greenland may be contributing to what we're calling the cool blob that right now is sitting out in the North Atlantic. So this plot is of the North Atlantic. We've got Greenland on top here. Here we are down in the far left corner. And this is showing the anomalies in surface temperature, the differences from normal and surface temperature. This was back in September. But it looks basically the same right now. And you can see this big area of cool water in the North Atlantic. And there's been some very recent research by some people at Potsdam University in Germany suggesting that the extra meltwater from Greenland may be one of the major reasons for this freshwater plume out there. And as I'll talk about in the end, I think this is also playing a role in affecting the jet stream and the weather changes that we're experiencing. Notice also the very warm water temperatures off of the East Coast. And that's partly because when you add this extra fresh water in the North Atlantic, it slows down the formation of deep water in the ocean, which slows down the whole ocean current system. And it kind of like backs up the Gulf Stream. And so that's partly why we're seeing all these warm waters off of the Arctic coast. And then finally, we can look at permafrost. This is the third permanent ice type up in the Arctic. And over the years, people have been studying the temperatures of boreholes in the permafrost up in Alaska. And if we focus on these very high latitude boreholes in northern Alaska, and we look at how the temperatures have changed with depth. So this graph goes down deeper and deeper into the soil, starting in 1976, going to almost present. And what we see is that at all these different locations here in North Alaska, the temperatures are all rising. And this is a concern for many reasons. As the permafrost degrades, it challenges infrastructure in the area, but it's also a concern because we know that it's going to release carbon.
Muted.
From carbon dioxide, if there's oxygen around, or methane. And these are, of course, both adding to our greenhouse gas problem. And then there's the sea ice. So as I'm sure you've all heard, the sea ice is disappearing. But we can look back actually about 1,500 years with this work done by Kennard a few years ago. And based on the sediments at the bottom of the Arctic Ocean, they can estimate how much sea ice there was in the summertime floating around on the Arctic Ocean. So as we look back in time, we see that it does change, year to year, decade to decade somewhat, but it stays relatively steady. This doesn't have the modern record on it yet. If we put the modern record on there, we can see that the change that's happened in the last few decades is really unprecedented in this time period. But this only goes to about the early 2000s. In 2012, we set an all-time new minimum amount of sea ice record in the Arctic. And if we try to put that data point on this chart, you can't even put it on this chart. And you might have heard that since 2012, the sea ice has regrown and that everything's fine. We don't have to worry about it anymore. So let's put the last few years on here. So what we see is that 2013 and 14 and 15 are all right down there too. So clearly the sea ice has not recovered in any meaningful way. And I should mention that right now, in the month of January that just passed, we set an all-time new minimum record for January. The least amount of sea ice ever seen in January right now as we speak. So over the last 30 years, we've seen a decline in the area of sea ice by about 50% in 30 years. And the volume, if you multiply that area times the thickness of it, it's declined even more, something in the area of 60%. So this is a very fast change, and it's a huge change. The sort of silver lining to that cloud is that this is an icon of climate change. Anybody can look at this change in sea ice and be amazed. You don't have to be a scientist. This is a great hook with the public because they can look at that and just really understand that the changes that are happening to this Earth are absolutely amazing. So just to drive that point home a little more, we have this animation that was created by the group at NOAA and NASA. And what it's showing us, let me stop it so we can talk about what you're seeing here. We're up at the Arctic now. You can see Greenland and Alaska and Eurasia on top. And the colors there are telling us about the age of the ice that's floating on the Arctic Ocean. So you can see the scale on the right side of the window there. The white colors are all ice that's very old, so something on the order of 8 to 10 years old. And the bluer the color, the younger the ice. And it turns out that as ice gets older, it also tends to get thicker. So when you look at this, you can think about the white colors being really thick ice and the blue colors being young, thin ice. So when we put it in motion, you're going to notice a couple of things. You're going to notice that the ice moves. It rotates basically in a clockwise direction on average around the Arctic Ocean. And you're going to notice that every year the blue ice grows and then it shrinks back in the summer. So you'll see this kind of pulsing going on as the years go on. You can see the time scale here. We're starting in 1987, and let's put it in motion. Okay. So it sort of looks like an organism up there. And so what you notice now, you've got about, say, half of the Arctic Ocean, or a third maybe, has quite a bit of that thick old ice in it. You can see how the ice rotates around the Arctic Ocean and eventually gets spat out along the east coast of Greenland, where it melts in the North Atlantic. You can see that it generally is thicker over on the Canadian side and over towards Alaska, where it tends to get piled up by the average wind circulation. And now as we get into the late 2000s here, we start to see some very big changes happening. Try to stop it. Oh, no, stop it. Oh, well. Anyway, so I think what you saw was all of that thick old ice basically disappeared just in the last really decade or so. Smells not cooperating.
It was originally.
All right. So why do we care about this sea ice disappearing so rapidly? Well, there's a lot of reasons. One of them is that there's a whole ecosystem up there that has basically adapted to having the Arctic Ocean filled with sea ice. And as it disappears, a lot of these animals, including the people who live up there, are being very adversely affected. In fact, one of the things that's happening is that some of the coastal towns up in Alaska and other places, because the ice has retreated so far, now when a storm comes through, it generates a lot bigger waves on the Arctic Ocean. So they're seeing a lot more erosion, and then you put on top of that sea level rise, and some of these towns are actually going to have to be moved. The other reason we care about the sea ice disappearing is, of course, sea ice is very white. And what we're showing here is that what the sea ice looked like in 2012, that record year, compared to what the average was for the previous 30 years in Cape. And obviously there's a huge decline. And the reason that's important is because all that white ice that used to reflect a lot of the sun's energy right back to outer space, now instead is going into the ocean, where it's absorbed. And it heats the ocean, and it enters the climate system, whereas before, it just went back to outer space and never warmed anything. So this is one of the reasons why the Arctic is warming so fast. We've got all this extra energy from the sun going into the areas of the ocean where there used to be ice, and now it's warming that ocean, which then warms the atmosphere. So we see the Arctic is warming 2 to 3 times faster than just about everywhere else on the planet. We can see that if we look at the air temperatures up there as well, compared to what's going on in the middle latitudes. So going back to the late 1940s, the blue line here is showing how the temperature has changed in the middle latitudes where we all live compared to what it's been doing in the Arctic, which is the turquoise line. And what you see is, of course, the Arctic has been warming much, much faster. We call this amplified Arctic warming. Why do you care that it's warming so fast in the Arctic? Well, let me try to explain. One of the reasons, at least. So if you think about a layer of atmosphere that extends from here in mid-latitudes, here in Washington, D.C., all the way up to the Arctic. We know that it's much warmer here in general in Washington than it is in the Arctic. And we also know that air, when it warms, expands. So this layer here in Washington is going to take up more room. It's going to be thicker here than it is up in the Arctic. And this creates effectively a hill in the atmosphere. If you think of a blob of air sitting on top of this layer, it wants to flow down the hill, just like water wants to flow down the side of a mountain. And that creates a wind. But because the Earth is spinning, that wind gets turned to the right. Everything that moves on the Earth in the northern hemisphere gets turned to the right. And this creates then a wind that we call the jet stream. And it's because of this difference in temperature. But now think back to this amplified Arctic warming. We're seeing the air warm much faster in the Arctic than it is here in Washington, D.C. And so the thickness of that layer is changing much faster there in the Arctic than it is down here, effectively making that hill less steep. So there's less force driving that wind, which is causing the jet stream to become weaker. And we know that when the jet stream is weak, it tends to be wavier. And the reason is because when it encounters an obstacle of some form, like a mountain range or a blob of hot air sitting over a desert or something like that, it's more easily deflected than when it's strong. That's one of the reasons. So we see a weaker jet stream becoming wavier. Why do you care about that? Oh. It was working just fine before. Okay, so you can imagine these two panels on the right here are supposed to be animations. They were going just fine earlier, about half an hour ago. The upper one is showing you small waves in the jet stream, and if it were working, you'd see that they would be moving quite rapidly from left to right, from west to east. But down in the bottom right here are waves in the jet stream that are much larger, and this is what we expect to see happen as the Arctic warms up. And we know that when those waves get larger, what you would have seen is they move much more slowly from west to east. Okay, so you have to use your imagination here. Why do you care about those waves moving more slowly? Well, it turns out that these waves in the jet stream are what create our weather. So here's a typical wave in the jet stream. It looked a lot like this for the last 3 years, with a big northward swing, which we call a ridge over the eastern Pacific, and then a big southward dip over the middle of the country. So the reason these waves are important, for one thing, you see that the jet stream separates the cold air to the north from the warm air to the south. And so depending on whether you're north or south of the jet stream determines whether you're in air mass or a warm air mass. But these waves in the jet stream are what create the dynamics in the atmosphere that create nice weather in this part of the wave. So when the winds are coming from the northwest, that tends to cause high pressure, clear blue skies, drought in California. And this part of the wave, which is where we were most of last winter and the winter before, is where it's wet and stormy. Okay? So these big waves tend to stay in place a long time. And if you're in, say, the wet and stormy part, like Boston was last year, the parade of storms ripples through these big waves and brings the snowstorms that we had last year. All right, so now I want to show you what the real jet stream looks like. I don't know what's going on with this mouse here. So this is an animation created by NASA's Science Visualization Studio using real winds, showing from high up in the atmosphere, the jet stream level, where the colors are red and yellow is where the wind speeds are strong. And you can clearly see with your eye where the jet stream is, all those crazy north and south swings. So this is what it really looks like. And what I want you to notice is, first of all, just how chaotic it is. I'm going to run it one more time, I hope. You can see all these swirls of different sizes and shapes, and think about, as a scientist, trying to measure whether they're changing. How do you go about doing that? You can also see times when the waves are big like this, and you can see how they tend to stay in one place for a long time. So it's a nasty creature to deal with, but it's also a very interesting one. Okay. Oops. Okay, so the research that I'm mostly focused on now is trying to figure out whether, in fact, we're seeing this gnarly, chaotic jet stream taking on a more wavy character like this one is. Whether those waves are getting bigger, or perhaps these wavy patterns are happening more often. It's kind of two ways to look at it. And whether we can, if we do see some changes, whether we can tie it back to what's happening in the Arctic or not. So one of the ways we're doing this, I'm just going to give you a very simple taste of some of the work that we're doing and trying to come up with some new metrics for measuring sort of the shape of the jet stream. It's not something that people have thought about much before. So you can think of this layer of atmosphere that I was talking about before as a topographic map. All right? So you guys probably, some of you are hikers, you look at topographic maps, you know that when the heights are high, you're on top of a mountain, so when these colors are red, it means that layer of atmosphere is very thick, and where the colors are blue, it's where the layer is thin, and of course we know that means that's where it's cold, and obviously it's colder in the Arctic than it is down here. But also, where these lines are very close together, as a hiker, you'd know that that means that the land is very steep. And this, when this hill is very steep in the atmosphere, that's where we find the jet stream. So we can use these lines of this topographic map to try to measure the waves in the jet stream. So if we zoom in now on a particular case, this is a day in January of 2014 when the polar vortex attacked us. You can see North America there. And here's one of these big northward swings, which we call a ridge, and southward dips, bringing all that cold air to us in the eastern half of the U.S. And again, we're looking at this topographic map of this layer. So what we do is we take one of these lines, okay, that tends to be right where the strongest jet stream is, or where the strongest winds are, where the lines are closest together. And every day, we keep track of how far north it goes and how far south it goes. Very simple. And every time that distance exceeds a certain value, we call that a big wave. And so we keep track of those every single day, we count them up, and then we look back in time and see whether they've changed. So if we do that now for the whole northern hemisphere in the fall, and see how the frequency of these very big waves in the atmosphere has changed, that's what the green line is. So going back to the late 1970s to present, the green line is showing us that the frequency of these very wavy patterns is in fact increasing. Also plotted on here, the black dotted line, is how fast the west to east winds in the jet stream are blowing. And remember, we talked about that hill getting less steep, causing the jet stream to get weaker. That's showing us that that is happening too. So recently, what we've been thinking about, though, is how to connect this back to the Arctic. There are a lot of things that can affect the jet stream and to make it be wavier or less wavy. So this is a new hypothesis that we've been working on, and I call it takes two to tango. The idea is this. So here's a map of the Pacific Ocean. You can see North America on the right. The Arctic's up on top there. And back in the good old days, the Arctic was filled with lots of sea ice. You can see it's right up against the coast. So if a wave in the jet stream came along, really not much, it didn't have any real interaction with the Arctic because that ice wasn't changing. It was pretty steady all the time. But fast forward to today, when we've got these cases where we lose ice, say in the Pacific part of the Arctic Ocean there. We know when that happens, a lot more heat goes into the ocean, it warms that ocean, and that in turn warms the air above it. Okay? So what happens when a wave in the jet stream comes along that looks like this? Well, that peak in the ridge there isn't located where that heating is happening in the Pacific part of the Arctic. And so there's really no impact on that ridge. But if the wave happens to show up here, and that should look familiar to you now, that big ridge that caused the California drought and the big dip over the east, when you lose that ice in that location and the ridge is located there too, what happens is that extra heat released back into the atmosphere is now making that ridge more intense. And now you know that when those ridges get more intense and those waves get bigger, they move more slowly. So this pattern then becomes more persistent. That's the idea. All right, so wrapping up here, I promised you I'd get back to those that contrast of years from last winter and the winter of 2012, and we're going to look at how the jet stream was different in those 2 years. So here's March of 2012 and how the surface temperature anomalies or differences from normal looked in that particular March. You can see that the eastern two-thirds of the country was way warmer than normal. Compare that to the first half of February last winter, and what you see is just the opposite. Those blues and purples on the east are all telling us that it's very cold, and of course California we know was very warm and dry, as was Alaska. So you can probably imagine in your minds what the jet stream must have looked like in these two cases, now that you know all about the jet stream. And as you'd expect, in the March 2012 case, what we had was a trough, a big southward dip over the west, and this huge ridge over the east. Note how big that wave is. And then, of course, in last winter, we had just the opposite, that big ridge over the west, big trough over the east. But in both cases, those waves were huge. And in both cases, those patterns were very persistent. So this is the story I'm trying to get across, is that we know the Arctic is warming really fast. We know that the ice is disappearing, and we know that it's slowing down the west and east winds of the jet stream. We have some evidence that it is causing these waves in the jet stream to either grow or be large more often. And when that happens, we see these very persistent weather patterns that can lead to extreme weather events. This is the chain of events that we think is leading to these increasing persistent weather patterns. Okay, so finally, I'm going to talk about what's going on right now, because it is just absolutely fascinating what's going on right now. We are literally sailing in uncharted territory, and let me explain why. So here again, we're looking at temperature anomalies or differences from normal for the last month and a half, so from January 1st right through a few days ago. Those red colors, of course, are telling you where it's warmer than normal, and the blues are where it's colder than normal. You can see North America and South America, the range is on the left. So I want to point out some features. Okay, we know El Nino is happening, right? It's there, that characteristic tongue of warm temperatures sticking westward from South America. We also know that it's very warm off the west coast of North America. This was called the warm blob last year when it formed. And it's been waning a little bit, but it's clearly still there. It's very, very warm up there. This is not normally occurring at the same time that El Nino does. This is an interesting combination. What else is happening? I mentioned that cool blob over in the North Atlantic. That has never happened before in conjunction with an El Nino. And then we have this just ridiculously warm Arctic. Some of those temperatures are like 20 degrees warmer than averaged over a month and a half. It's just crazy. So we're thinking back to that layer in the atmosphere that I talked about. And I remember I said when that layer gets changed in the hill that it creates is what changes the winds. So all of these anomalous temperatures that we're looking at around the globe in these very large areas of ocean that are just way either warmer or in one case colder than normal, they are all having their impacts. And I think that one of the reasons El Nino has not had the impact on California that was originally thought is that we've got this warm blob to the north. So instead of El Nino creating a stronger jet stream, which is what usually happens when you warm it to the south, so that would be tilting that, making that hill more steep. Instead, you have this warm water to the north, and so it's not having as much of an effect as it did, as it was expected to have. And then the Arctic as well, contributing to that. So it's affecting the jet stream in its way. So we've just got this incredibly unusual combination of factors all going on at the same time. So I think what we're going to see, my forecast for the rest of the winter, is going to continue to be very interesting. So as I said in the beginning, one of the silver linings to this cloud is that the public is really noticing that things are changing in their world. People love to talk about weather, and so it's a great hook for the public as well in connecting these extreme events to what's happening in the climate system. And of course, we have these people hanging out in the anti-science bunker, and I'm sure some of you people here in Washington know a few of those. The public is realizing this is going on. They're wondering, why the heck aren't we doing something about it now? I mean, climate change is affecting people today. This is not this gradual change that's going to happen to their grandchildren. It's happening now. So, part of the good news, I think, is that these people hanging out in the anti-science bunker have just run out of ammunition. But we'll see. So finally, I just wanted to end with showing you what today's jet stream looks like. Hopefully. Yes. It worked earlier. Come on. There we go. All right. So I don't really want to point out any particular features. I just want to show you how beautiful our jet stream is. And it's a very complicated thing, but it's also just a fascinating part of our climate system to be studying. So I'll leave you with that. And just one final note I want to say is that if you were registered to attend this, you're going to be getting a survey from Arcus afterwards, I believe. And I know that a lot of you here are working on at the intersection between science and policy. And if you are so inclined, there's going to be a question on the survey that asks if you would like to be join in a discussion with a member of the SEARCH community, which is the study of environmental Arctic change, and talk about either your experiences or your interest in how we get science knowledge into the hands of decision makers and any successes or lack thereof that you've experienced. So with that, I thank you so much for coming.
Thank you.
We want that thank you screen.
Thank you very much, and hopefully you're willing to take a few questions here.
Absolutely.
So does anybody have any questions in the room or online? If you have questions online, please enter them in the questions box. Otherwise, anyone in the room have any questions? Yes, Igor.
Can you give any comments regarding difference in climatic changes in sea ice in wintertime and in summertime?
Yeah. Yeah, those the effects on sea ice in the two seasons are actually very different from each other. So in the summer, obviously, we have sunshine, and one of the biggest factors that is driving sea ice loss in the summer is the fact that when you lose some ice and you expose some open water, you're absorbing more of that sunshine, and that's warming the water around the ice, which melts more ice, opens up more water, and we call this positive feedback. But what we're learning is that in the what sort of earlier in the spring is when the stage gets set. We're learning that these impulses of water vapor, which create more clouds in the spring, are starting the melt process at different times in different years. So in years when we lose a lot of ice in the summer, it tends to occur when we have springs that have one of these big pulses of warm, moist air up into the Arctic. And that starts the melt process, either earlier usually. And once the ice starts to melt, it actually darkens quite a lot. So it absorbs more sunshine when it's actually has started melted already. So that's just some new research that's coming out, is looking at how do we predict what the summer ice is going to actually do by the end of the summer. In the winter, it's some very different processes that happen, and it's different on the Atlantic side versus the Pacific side. Most of the Arctic, the ice grows until it hits the coast, and it's confined. It can't grow anymore. So really the only places where the ice can vary in its extent are in the open sections, which is over in the Bering Sea, over between Alaska and Russia, and in the Atlantic sector between Greenland and, say, Scandinavia. And it turns out that on the Pacific side, winds are the most important component over there. So variations in the winds during the winter season. Whereas in the Atlantic sector, it's more about what's happening with sea surface temperatures. And if you have a warm year with a lot of warm water moving up there, then that's when you tend to get big ice losses up there. This year is a great case in point, because what we've had is this a storm track running along that cool blob in the Atlantic, bringing all those storms into the UK, and those storms also bring a lot of heat and moisture with them, and they've been driving that ice loss up north of the UK and Scandinavia, up in that region. That's where the ice is really reduced this winter.
Great. I have a couple of questions online. The first one is the presentation going to be available on the web? And the answer is yes. You go to the website where you signed up for this seminar, or you can go to the ARCIS homepage at www.arcis.org, and we will have the presentation up within a couple of days. Also, another question is about the plot of the Greenland ice mass. Showed leveling off in the past couple of years, and do you have any explanation for why that might be leveling off?
It's just random fluctuations. It was relatively cold in Greenland the last couple of years, although 2015 was a record melt, another, not quite as bad as 2012, but it was a big melt year in this past summer, which was not on that graph. So again, we see these wiggles in these trajectories of what's happening with sea ice and with permafrost, and it's also true with Greenland. It's just there's some random variability that's on top of the overall trend.
I think what we call in the scientific world is a lot of noise in the system.
Yes, that's noise.
So with an improved network of global observations over the past 30 years, how do we know that more extreme weather isn't simply due to better observations and more observations?
Well, so extreme weather events, I mean, most of the work that I've been doing has been looking only back till the late 1970s or so, which is when satellite information was became available and became incorporated into our global atmospheric data sets. And really, there hasn't been a huge change in the amount of data since then. In fact, in terms of actual weather stations, they've been going down in number. But so over this period, we're clearly seeing changes in extreme events. They're measured in many different ways. There's really no reason to think that that the quality of the observations is affecting those numbers, especially since the late 1970s.
Okay, thanks. Here's another one online. Unless somebody, yeah, go ahead.
Chris Crawford from Maryland and NASA Goddard. My question is, I follow your work with great interest in the subject. And what I sort of understand early on is, my first, did you ever have any moments in sort of putting together your conceptual way of thinking about this problem? Ever sort of run into the idea, wow, this might be difficult to have a science, was it ever challenging to understand that there may be initial pushback on the idea, and then how the scientific community can continue to have a robust conversation about separating the signal from the noise, and how that weaves its way with natural variability, and then how we don't let that confuse the main message that things are really changing dramatically. And I just wondered if you had any thoughts on that.
For the sake of people online, maybe we could summarize the question as how have you had any thinking about the signal as something that's how do you make that case? I think is the question.
Yeah. Well, clearly that's a big problem in doing this work with the real world, because one of the things I forgot to mention when I showed you that temperature plot and how the Arctic had warmed so fast relative to mid-latitudes, it's really only since the late 1990s where this signal of Arctic amplification or amplified Arctic warming has emerged from the record. So we have a very short period of time over which to try to tease these signals of things like the waviness changing from the real world. So a lot of work now is going into using models to look at some of this stuff. And so some work that I've been involved with lately has been, for example, looking at how a natural fluctuation, say, in the Pacific Ocean sea surface temperatures, a fluctuation called the Pacific Decadal Oscillation, when that fluctuates and there's lots of ice in the Arctic, how does the atmosphere respond? And then if you do the same thing, same experiment, but reduce the ice a lot, do you see differences in the atmosphere? So those are the kinds of experiments that need to be done to try to isolate these effects in such a chaotic system. But you're right on. And a lot of the controversy surrounding this hypothesis has been related to really trying to tease it out of the real world. But as we move forward into modeling experiments, it's becoming clearer.
Great. So I have an online question here. It says, how do you reconcile your hypothesis with the results of Schneider et al., I hope you're familiar with Schneider et al., who demonstrated that there's a large-scale reduction of the near-surface temperature variance in northern hemisphere mid-latitudes, especially in winter?
Well, I think this is related to the previous question because clearly there's all kinds of things changing in the climate system. Some of them are part of the forced change or the human-caused climate change, but other things are these large-scale natural circulation changes like El Niños, like PDO, like there's a similar one in the Atlantic. So again, it comes back to how do these natural fluctuations in the system interact with this new thing that's happening in the Arctic that wasn't there before. So I'm not saying that the Arctic is taking over all these other things that are happening in the world. We've got to figure out how this stuff is all interacting with each other.
I like your metaphor of the tango, right? That there's a dance of all of the
Exactly.
New factors
That's
and
the
the existing ones.
Exactly. Yep. Yeah. So something like the PDO shifting can set up the ridge in a certain place, or it favors having a ridge in a certain place. And if there's ice loss there to go with it, that's when you get an interaction.
Do climate models correctly describe changes in jet stream path and intensity?
They are all over the map. There was a recent paper by Elizabeth Barnes and Renzo Polvani comparing a bunch of the climate models and how they simulate changes in things like waviness in the jet stream. And some of them have increases in waviness, some of them have decreases, and so I think we're really not sure whether the models are able to capture some of these types of features, and whether the interactions that we were just talking about in a changing climate system are being captured well either. I think that's an open question.
Okay, well, I think that may be all the questions that we have online. So why don't you all join me in thanking Jennifer again. And I'll invite you to come to our next seminar, which is going to be on March 31st, featuring Dr. Jeremy Mathis. He's going to be talking about ocean acidification. It'll be happening right here in this room and online. You can register at the same place that you registered for this one. It is online, and registration is open right now. Also, invite you again to consider becoming members of ARCIS if you're not already. We're the consortium that's representing you and helping you to advance Arctic research across boundaries. And other than that, I will, unless there's any other questions, I will wrap up. And thank you very much for spending your time here. Please be sure to fill out the survey that you received or will receive once you sign off of the webinar. Thank you very much, and have a great day.